What's up guys, Patrick here, welcome back. Moving on to the next example, we got a limit as x approaches positive infinity of 3x times tan of 4 over x. So like usual, let's do a direct substitution. Let's see what's happening with these two functions that are multiplying by each other. Notice this function is going to go towards positive infinity. And then this here is going to be tan of 0, because 4 over infinity is going to go towards 0. Then tan of 0 is just 0. If you remember the tan graph, the way it looks as a quick little review, we got pi over 2, negative pi over 2. It looks like that. All right, so at an x value of 0, the function is 0, the y value is 0. So notice this is an indeterminate product, so we can't tell what the limit's going to be from just doing a direct substitution. So we got to apply a different strategy, and with an indeterminate product, what we want to do is convert it to an indeterminate quotient and then see if we could apply L'Hopital's rule. The question is, are we going to bring this tan of 4 over x to the denominator and work with its reciprocal, or would we bring this 3x down to the denominator and work with this reciprocal? And I feel like bringing this down is easier. And actually, we don't even actually have to bring down the whole 3x. We could actually factor out a 3 first. So let me actually do that first. I think it's going to be easier. I should have mentioned that at the beginning maybe. So I could take out this 3. Notice this is still going to be infinity times 0. And then what I would do is I would rewrite this as tan of 4 over x over 1 over x, like that. I feel like this is easier to work with than 1 over 3x. It's not a big deal. You're still going to get the same answer, and it's not a big deal working with this and taking this derivative. But I just feel like it's easier to take the 3 out here and then just work with 1 over x. All right, so from here now, this is going to be 0 over 0. 1 over infinity goes towards 0. So we're going to have 0 over 0, indeterminate quotient. Let's apply L'Hopital's rule on that. So the 3 we would keep on the outside. We'd have the limit as x approaches infinity. Now the derivative of tan is secant squared. That inner function is going to stay the same, but now we got to take the derivative of 4 over x, which I would rewrite as 4x to the negative 1, negative 4x to the negative 2, negative 4 over x squared. That is the derivative of 4 over x. So we'd have negative 4 over x squared. And then 1 over x, if we applied this same thing, x to the negative 1, there wouldn't be a 4 here. Bring the negative 1 down, then it'd be negative 2. So this, the derivative of that would just be negative 1 over x squared. All right, so we applied L'Hopital's rule. And then from here, we're dividing by this fraction. So it's like multiplying by the reciprocal of that fraction. So I'm going to take that, put x squared over negative 1. Notice the x squareds here cancel out. Negative 4 divided by negative 1 is positive 4. And then I could actually take that positive 4 and bring it out. So then we'd have 4 times 3, which would be 12. Kind of skipped some steps there, but hopefully you see what happened. I just took that 4, negative 4 divided by negative 1 is positive 4, brought it out, got to multiply by this 3. So that turns into a 12. And then we would end up having secant squared 4 over x, which is going to be like secant squared of 0. Okay, now secant squared of 0 is like 1 over cos squared of 0, which is like 1 over cos of 0 squared. Cos of 0 is 1, 1 to the power 2 is 1, 1 divided by 1 is 1. So this whole thing, this whole limit actually is going towards 1. So we'd have 12 times 1, which ends up being 12. And so that is the answer to that limit there. Right? So just another example of where we took an indeterminate product, changed it to an indeterminate quotient, applied L'Hopital's rule, and then we were able to get the